Hello everybody, my name is Max Wamsley from the Dongmao Zhang lab at Mississippi State University, and today I'll be presenting Back to the Drawing Board, a unifying first principle model for correlating sample UV-Vis absorption and fluorescence emission. If you have any questions or would like to skip to a specific section, please check our YouTube description down below for the timestamps. First, I'll give you a quick overview of absorbance and fluorescence. Absorbance spectrophotometry and fluorescence spectroscopy have been used extensively for nearly 100 years. They are two highly utilized methods in chemistry, biology, and material science. Absorbance involves the measurement of the total light extinction or the light lost after passing through a sample. After absorption, fluorescence emission can occur. Fluorescence spectroscopy is the measurement of the emitted light after photoexcitation. The reason spectroscopy methods are so utilized is because they are cheap, easy to use, and have a high versatility. However, there are many complicated photophysical phenomena that are involved in absorbance and fluorescence, which commonly leads to spectral misinterpretation. Understanding the relationship between absorption and fluorescence emission is important to help understand the fundamental photophysical properties impacting various materials. Obtaining an absorbance and fluorescence spectra is extraordinarily cheap, simple, and predictable. However, there are many complicated phenomena that can impact spectral acquisition. Therefore, extreme care should be taken when analyzing and obtaining absorbance and fluorescence data. Shown here is a simple diagram of UV-Vis spectrophotometry. We first excite the light, shown as lambda x, and measure the total light extinction as the beam passes through the sample. The spectrophotometer measures the fraction of the transmitted light that hits the detector, which can be measured as transmittance or absorbance. Absorbance is most commonly used for the UV-Vis measurements, which is what we will be using here. Beer's law is a common equation used to describe the relationship between chromophore, concentration, the path length, and the molar absorptivity. Beer's law states that the absorbance is a product of these parameters and is linear with concentration. However, we cannot simply accept Beer's law for all situations. This is because, in many cases, Beer's law will fail. Beer's law is only applicable for a pure fluorophore at a reasonable concentration. Therefore, we have to take into account the exponent for scattering and the term for absorption. After absorption occurs, fluorescence may also take place. Fluorescence is the emission of photons upon photoexcitation. Unlike absorption, fluorescence emission is detected at 90 degrees from the excitation in a commercial spectrophotometer. This is because light emission occurs in all directions, so we detect the photons at an angle where the excitation beam won't impact and interact with the detector. The textbook model shown here is used to correlate the absorption and fluorescence emission. This equation takes into account the instrumental parameters and the quantum yield of the analyte, which is denoted as K. The second part of the equation represents the amount of absorbed photons at an excitation wavelength that can be emitted. According to this model, the fluorescence will continually increase just at a reduced rate. However, this is not an accurate representation of the trend that occurs. This is because of a photophysical phenomenon called the inner filter effect, which has to be taken into account. Shown here is the impact of the inner filter effect on rhodamine 6G. The absorbance of rhodamine 6G with increasing concentration is shown here in the insert. And you can see that the rhodamine 6G concentration increases linearly with absorption. However, the fluorescence of rhodamine 6G with the same concentrations increases at a different rate and also has a peak shift. The observed intensity at the peak absorbance of 535 nanometers is shown here as a function of the fluorescence intensity. We can see that there is a small, short region of linearity followed by a decrease rate, which then reaches a maximum. At this maximum point, which is only at an absorbance of 0.25, the intensity starts to decrease with increasing absorption. The textbook model for fitting the absorbance and fluorescence, which was mentioned before, is shown by the black line. This highlights the poor fitting of the previous model. It is really easy to see, compared to the actual data and experimental model, that there is strong deviation due to the inner filter effect in real-life experimentation. Many inner filter effect correction methods have been attempted, and some with great success. To correct for the inner filter effect, we first need to understand the processes that cause the inner filter effect to take place. Shown here is a model of a cuvette containing a sample that is undergoing excitation. Upon excitation, which is denoted lambda x, emission occurs in all directions at all points in the cuvette, which is shown by the red sphere. However, only the fluorescence at a specific region and at a specific angle can actually reach the detector. We call this region the effective sampling path length, which is denoted as LS. The emitted light at the effective sampling path length then goes through a monochromator to the detector at a specific emission wavelength, lambda m. However, if the sample has significant absorption at lambda x and at lambda m, light can be lost before it is detected. This is represented by AX dx for the absorption occurring at the excitation wavelength across the excitation path length, and for the absorption at the emission wavelength across the emission path length. Our lab has previously developed a method to detect the excitation and emission path lengths that can be obtained using a commercial spectrophotometer and a very easy water Raman method. This method has been summarized in a previous video by my lab mate Samadhi, so feel free to check it out to understand how to calculate for dx and dm used in this equation. Now I will quickly walk through a summary of the model derivation and validate the model for you. If you would like to have a more detailed understanding of the model derivation, please feel free to check out our manuscript. For simplicity, we'll assume that all samples are measured with a cuvette that has a path length of 1 centimeter. Equation 1 shows all parameters that can impact a sample that is undergoing excitation in a commercial spectrophotometer. LS, DX, and DM are all viewed as the path length in centimeters for a pure fluorophore. The first term in equation 1 is the excitation intensity before entering the sampling region, where IX is the excitation power, AX is the absorption at the excitation wavelength, DX is the excitation path length, and LS is the effective sampling path length. The 10 to the negative AX term will remove a fraction of the excitation power based on the absorbance at the excitation wavelength, the excitation path length, and half of the sampling path length. The second term accounts for the total absorbed photons in the sampling region by using the effective sampling path length times the absorbance at the excitation wavelength. The 1 minus 10 to the negative AX term, when used, is the amount of photons that are absorbed and available for emission. These two terms, once multiplied by the quantum yield, will depict the intensity of emitted photons by the fluorophore inside of the effective sampling path length, as well as the photons removed due to the absorption at the excitation wavelength. Next, we have the fluorescence intensity attenuation due to the fluorophore absorbance at the emission wavelength, which is denoted AM. This is multiplied by the emission path length, DM, as an exponent term. Again, the 10 to the negative AX term represents the photons lost at the emission wavelength across the emission path length. Finally, we multiply the entire equation by the instrument responsivity, which is a fraction that encompasses the effectiveness of the instrumental parameters at detecting the emission. If the effective sampling path length is less than or equal to 0.46, then we can simplify to equation 2 using basic algebra. This equation is easily met in practical applications because LS is very small compared to a 1 centimeter cuvette. Combining the 2.303 I term here, shown in the box, gives us equation 3, where K is a constant that represents all parameters using a singular instrument and sample. Now I will show you the accuracy of the model for a pure fluorophore rhodamine 6G to validate its accuracy. Shown here is the absorbance and corrected fluorescence for the previously shown rhodamine 6G. Again, you can see a consistent linear trend with increasing concentration of absorbance shown in figure A. In figure B, you can see that with using the inner filter effect correction model, we are able to linearly correlate the fluorescence intensity with absorbance across all wavelengths. The trend for this correction can be seen here in the insert, where you see a very linear trend of corrected intensity compared to absorbed intensity. Figure C shows our fitting, as well as the previous fitting, at the absorbance peak of rhodamine 6G. The black line represents the previous textbook model, and the red line here represents our model. You can see that our fitting almost perfectly matches the fitting of the observed fluorescence intensity, validating the model for pure fluorophores. We are also able to correlate the fluorescence intensity in a sample containing other absorbing species. In this example, I showed the correlation of a chromophore-fluorophore mixture using our model. The only difference in this equation is that the pure fluorophore contains differing concentrations of pure absorbing species. Therefore, we have to modify the equation from AXF to AXS to account for all sample absorption. To achieve this, we obtain an absorbance and fluorescence spectra for the pure fluorophore, and then we obtain the spectra for the analyte of interest containing the chromophore as well as the chromophores by themselves. Here we have DNPH and MBI, which are two chromophores with no fluorescence, as well as 2AP, a fluorescence active chemical. You can see that MBI and DNPH, the two absorbers, have differing absorption locations. The dashed line in figure B shows the wavelength region where we excited the sample, and the highlighted region is the region where fluorescence emission takes place. Figure C shows that 2AP with a concentration that remains the same has a decrease in fluorescence intensity with increasing MBI and DNPH concentration. And this is due to increasing inner filter effect or self-absorption by the sample. In figure D, when we correct for the fluorescence intensity, you can see that there is almost no change in the corrected fluorescence intensity with increasing chromophore or absorber concentration. Using our model, you can see that the corrected fluorescence intensity is nearly identical for all concentrations of chromophores. The mathematical model can also be used to study the effect of stimuli treatment on fluorescence intensity. Fluorescence signal is highly sensitive to experimental conditions, and understanding the effect of stimuli treatment is critical in biological and chemical sensing as well as for material development. Temperature on fluorescence is widely studied. In some cases, we would want a temperature-dependent fluorophore to have a higher sensitivity to detect a change in the fluorescence intensity. Under other conditions and in different experimental environments, we also may want a temperature-independent fluorophore to have more stable emission and ensure that no matter the condition, we can have the same amount of emission occurring at all times. By taking the ratio under two different conditions, we can simplify into equation 2 to study the effect of stimuli treatment on the quantum yield. The reason we're able to do this is because these are instrumental parameters that can be canceled out when using the same instrument. Equation 2 shows the ratio of a sample under differing stimuli treatment, Ts, compared to a reference stimuli treatment, Tr. Rearrangement of this equation leads to equation 3, where we have the ratiometric wavelength-specific quantum yield, or RWSQY, on the left side of the equation, and on the right-hand side, we have variables that are easily experimentally determined using a commercial UV-Vis spectrometer to get the absorbance, and a commercially available spectrofluorometer to get the corrected fluorescence intensity. This equation enables the quantitative decoupling of the effect of photon absorbance and fluorescence quantum yield due to changing stimuli treatment at any emission wavelength on the fluorescence spectrum excited at any wavelength. To our knowledge, this is the first time such information has been available. This ratiometric wavelength-specific quantum yield with a calibrated fluorometer detector can be expanded to study the effect of the fluorescence quantum yield across the entire wavelength region by simply taking the summation of the inner filter effect corrected fluorescence emission spectrum, which is represented by the integral in equation 4. Using the ratiometric wavelength-specific quantum yield, we wanted to study the impact of temperature on anthracene, a highly studied organic fluorophore. The temperature-dependent fluorescence of anthracene has been commonly studied due to its minimal change in fluorescence intensity with increasing temperature, making it a stable emitter under various temperatures. Increasing the temperature results in an increase or decrease of the absorption depending on the excitation wavelength, which we can see in figure A and B. The fluorescence can also increase or decrease at differing emission wavelengths when excited, as shown in figures C and D. However, since both the absorption and fluorescence is changing with temperature, we don't know if this change is due simply to anthracene having changing absorption or due to a change in the fluorescence quantum yield with changing temperature. This is because the fluorescence quantum yield is defined as the ratio of the emitted photons to absorbed photons. To solve for this, we can use our integrated ratiometric wavelength-specific quantum yield model to determine if the quantum yield is changing with wavelength and/or temperature. Shown here is 4 different excitation wavelengths for anthracene in the first row, as well as the integrated ratiometric wavelength-specific quantum yield at differing emission wavelengths shown in the second row. We can see that anthracene has a strong emission dependence on the quantum yield. However, the quantum yield does not seem to be dependent on the excitation wavelength. This can be seen by the quantum yield ratio having a similar trend for all excitation wavelengths. However, the emission wavelengths have a strong quantum yield dependence, where some wavelengths have an increase in the quantum yield and some have a decrease in the quantum yield, shown by the peaks and the troughs. These findings are fascinating because it shows that under differing conditions, we can either decrease or increase the quantum yield, which is useful for the development of anthracene in organic-based LEDs, or OLEDs. In summary, we developed a first principle mathematical model to reliably correlate the UV-Vis absorbance and fluorescence intensity. This allows us to formulate a function to correlate the fluorescence as a function of absorbance at a much larger linear dynamic range. In addition, it allows us to accurately determine and correct the fluorescence intensity based on the UV-Vis absorbance of the sample, allowing for more accurate and reliable fluorescence data acquisition by correcting for the inner filter effect. Using this model will significantly improve all areas of fluorescence analysis, where accurate determination of the fluorescence intensity is crucial. Finally, we rearranged our model to study the impact of stimuli treatment, specifically temperature, on the fluorescence intensity and quantum yield. Accurate determination of the wavelength-specific quantum yield has never been achieved before and could drastically improve material design for solar cell, nanoelectronics, and fluorescence sensing applications.
I will now show you all how to calculate the inner filter effect corrected fluorescence intensity for a basic sample rhodamine 6G. If you have any questions or would like to contact us, please check the description down below. To calculate for the inner filter effect corrected fluorescence intensity, we need the UV-Vis absorbance of the sample, the excitation and emission path length of the sample, as well as the observed fluorescence intensity. Shown here is a spectra of rhodamine 6G excited at 525 nanometers. Therefore, our excitation wavelength will be 525, and our emission wavelength will be the wavelength that we are measuring the fluorescence intensity at. First, we have to multiply the observed fluorescence intensity times 10, and make the exponent term AX times DX plus AM times DN. So our AX is at 525 nanometers, times our DM, which in this case has been calculated to be 0.47, plus AM, DM, and in this case AM is at 535 nanometers, times DM, which in this specific example is 0.56. However, we have to make sure we fix some specific calculations. We don't want the excitation wavelength to change, so we're going to set this B227 term to be fixed, and we do that by putting a money sign in front of each component. And same with the excitation emission path lengths, we don't want those to change either, so we'll fix those. This term we can keep the same because we want this term to change as we go down in Excel. So after doing that and double clicking here, we can see we have the corrected fluorescence intensity for rhodamine 6G at all wavelengths.